All right, so we have some leftover from section 9.1. Last Thursday, I emailed you pretty late to correct a mistake I made in the class. Yeah, I'm not sure if you have received my email. The email is about example 3 in section 9.1. So here I want to make it very clear. When the hypothesis test is one tail, either right tail or left tail, and the confidence level has to be 1 minus twice of the significance level. So in this example, example 3, since the original claim is p sub 1 less than p sub 2, it is a left tail test, so one tail test. Then we have to use this formula to find a confidence level. We use 1 to minus twice of 0.1. Significance level is 0.1. Twice of it is 0.2. So we subtract 0.2 from 1. We have 0.8. So the confidence level is supposed to be 80%. So that's the confidence level we need to apply when we use the interval to test the claim. Make it very clear. Let's see. Courtney, did I miss something or is there a reason everything on the homework has a due date? Oh, yeah, I also posted the announcement yesterday. That's what I normally do. By the end of the semester, I normally do 2 weeks, like within 2 weeks, 2 weeks away from the semester closes. I reopen all the assignments, and then if anybody has something has assignments uncompleted, they can catch up and boost their scores. All right, yeah. So am I clear about this example? Example 3? Very important. If it's a one-tail test, if the hypothesis testing is a one-tail test, oops, how do I find the? No problem, Kayla. Yeah, I want to make sure you understand what I'm talking about for example 3. If the hypothesis test is one-tail test, either right tail or left tail, then the confidence level has to be 1 minus twice of the significance level. Do you guys know what I'm talking about here? Yeah, I made a mistake and I apologize. The email explained some example 3. Okay, thank you, Kelly. I know you would pay attention. Okay, thank you, Miranda. Yeah. So no worry because we are going to see problems, similar problems in 9.2. But we do have a leftover from 9.1. So let's look at the last example in 9.1. This question. This is about two proportions, by the way. Let's read the question. A study was conducted to determine the proportion of people who dream in black and white instead of color. That's a very interesting thing, right? I never thought about your dream is black and white or your dream is colored. I never paid attention to that. Among 323 people over the age of 55, 68 dream in black and white. So I would say that's the first sample. For the first sample, we have 323 subjects. And number of success. Suppose dream in black and white is a success. Then the number of success is 68. So that's the first sample. Keep reading. Among 301 people under the age of 25, young people. So I would say that's sample 2. Sample 2, we have 301 subjects, and not bar. I'm sorry, not bar. Bar is mean. We are not doing mean. Yeah. Number of successes among the 301 subjects in sample 2, we have 14 of them. 14 of them dreaming black and white. Yeah. So that's the given information. Alpha is given is 5%. We need to test the claim, original claim. The proportion of people over 55. So the proportion for sample 1 is bigger than proportion for the second population. Yeah, P1 here is not for sample 1, it's for population 1. Population 1 would represent all the people who are 55 years old or above. And population 2 would represent the people they are under 25-year-old. Yeah. So P1 is bigger than P2. That's the original claim. So what are we going to do here in this example is we are going to apply all the 3 methods to test this claim. What are the 3 methods? We have 3 methods. The first method is critical value method. Critical value method. The second method is the p-value method. The third method is the confidence interval method. Yeah, we are going to apply all the 3 methods to test the claim to see the result. Okay, original claim is P1 bigger than P2. The older population has a higher proportion dreaming black and white compared with young generation, young population. So based on the original claim, we can identify the null and the alternative. The null is always P1 equals P2. The alternative is P1 bigger than P2. Yeah, those basics, at this point, those basics you should be very familiar with, because the original claim has to be either equal to the null or equal to the alternative. Since the null is equal, original claim is different from the null, then it has to be the same with alternative. Since the alternative is P1 bigger than P2, so this is a right tail. Right-tailed z-test, all right, since it's a proportion. Right-tailed z-test. On Thursday, I have shown you how do we use technology to process the hypothesis test, right? Yeah, the technology would help us to do critical value method and p-value method. The function we are going to apply in the calculator, do you guys remember what's that? 2 proportion z-test, right? Okay, let's go to our calculator. Everybody get it ready? We go to stat and the tests, and we are going to go down all the way down to find 2 proportion z-test, number 6 on my calculator. 2 proportion z-test. And we are going to enter the values for the following entry: x1, n1, x2, n2, and p1. Yeah, that p looks like a p-value. No, I mean actually it's this p. p1 not equal to p2 or less than p2 or bigger than p2. So the type of the test, and then calculate. So we are going to enter x1 equal to 68, n sub 1 equals 323, x sub 2 equals 14, n sub 2 equals 301. This is a right tail test, so we're going to highlight bigger than P2, of course, P2. All right, yeah, let me enter the values. X sub 1 is 68. X sub 1 is 68. Number of successes in sample 1. N sub 1, sample 1 size 323. X sub 2, 14. N sub 2, 301. And we go to write twice to highlight and confirm P1 is bigger than P2. That's how the calculator knows you are doing a right-tailed z-test. And then calculate. Let me tell you what do I have for the test statistic and a p-value. My test statistic is 6.059725845. My p-value is 6.843125 e to the power of -10. Yeah. So that basically tells us the p-value is super tiny. Yeah, we can run it to 0, no problem. Let me know, guys, do you have the same the same test statistic z and p-value? You should have the same thing with me. All right, very good. Thank you, guys. Perfect. So we don't really use the critical value that much, because if we use the function, we would have a p-value, and the p-value is very convenient to determine are we going to reject no or fail to reject no. Yeah, unless the question specifically require you to find the critical value, we don't have to go through that process. Yeah, we can make a decision using p-value. And also, critical value method and the p-value method are always equivalent. In a sense, they always give you the same result. Either both methods reject no, or both methods fail to reject no. Okay, so since our p-value is so tiny, it really doesn't matter what's your significance level. The p-value is low for sure, right? Yeah, p-value is low, no must go, so we're going to reject the no. For more conclusion, you can refer to the table I made for you, or at this point, since you have been doing the same thing many times, you should have an idea how do you conclude for the original claim, right? Yeah. Since we reject no, so we have sufficient evidence to support the original claim. What's the original claim? The older people, they do have a higher percentage dreaming in black and white compared with young people. Yeah, maybe because they grew up with black and white TVs. Yeah, I'm not sure. So that's the first part of this problem. Next part, we are going to use confidence interval method to test the claim. Yeah, let's see how does that work. Use confidence interval to test the claim. We would have found out the confidence level, right? We would have to figure out what's the confidence level. Okay, what is the significance level? Significance level is 5%, and then the test is a one-tail test. Yeah, now I'm gonna ask you, what's the confidence level supposed to be? Is that gonna be 95% or just 90%? Yeah, depends on have you read my email or not. Miranda is not 95%, is 90%. Let me make it clear. Is 90%. Yeah, I blame myself. My bad. Is 90%. Okay. Yeah, let me repeat why. You want to look at the email I sent you Thursday night, pretty late, because confidence interval is symmetric, kind of like a two-tail. So if the significance level 5% in this case fall in the right tail, that means you have 5% significantly high. Then if we make it as a symmetric thing, then we should have another 5% fall in the left tail. That 5% is significantly low. So the middle part, the confidence part, not significant part, would be 90% only. So here it is 1 minus 2 times 5%. It is 1 minus 10%, and that is 90%. Okay, I'll pause here. I want to make sure I do draw your attention here. When the significance level is 5%, depends on what type of test or what type of claim here we have. Since the original claim is right tail, the test is a right tail test, we have to make it a symmetric. So 5% in the right tail, 5% in the left tail. In the middle, we only have 90% confidence. All right? Let me repeat that. If your significance level is alpha, and your test is a one tail test, then your confidence level is 1 minus 2 alpha. 1 minus 2 alpha. Let me know. Did you hear me here?
Yes, that makes sense. So if it's a two-tailed test, though, you don't times alpha by 2 because it's sort of already incorporated into the problem?
Exactly. You're right, Kelly. Perfect. If it was a two-tailed test. But this one's right tail test is one tail, right? We have to double the alpha and then subtract 2 alpha from 1 to get a confidence level. Because confidence level is symmetric, kind of like a two-tail. Thank you, Melinda. Miranda, am I clear about that? It's very important though. It's very, very important. We don't mind to make a mistake. We make a mistake and then we correct it, and it's more impressive. Probably I will never forget it again, even when I'm tired or anything. Right? Bad thing could become a good thing. Very good. So if it's a one-tail test, and we must use 1 minus 2 alpha to get a confidence level. All right, so now we know the confidence level of the confidence interval estimated test we're going to apply. And how do we use the confidence interval method to test the claim? The function we are going to apply. Guys, let's look at our calculator. Stat tests is interval, right? Do we have 2 samples? What kind of interval? Is about the proportion, so it's gonna be Z interval. Do you see number 9? Number 9 is 2 sample Z interval. All right, that's the function we are going to apply to test the claim using confidence interval. All right, so I'm going to select that and hold on, not this one. Stat tests, 2 sample Z interval. Oh, my bad. To proportion, of course. I'm so sorry. To proportion. Let's go down. Letter B. To proportion Z interval. To proportion Z interval. Okay? Letter B. Not 9. Letter B. The function we are going to apply is a to proportion Z interval. To proportion Z interval. Okay, we click that, and we are going to enter the values. And you know what? You will notice the values we had earlier is here as well. I mean, earlier we used two proportion z-test, right? And we entered those values. I had it in orange. But when you go to the function two proportion z interval, you would notice those values are already in place. Do you have that same thing? I have x1 68, I have n1 323, x2 14, n sub 2 301. Yeah, they're already in place. You don't have to even repeat the entry, right? Yeah, C level, confidence level is 0.9, 90% 0.9, and then calculate. Let me write down my interval. Yeah, my interval is negative, sorry, not negative, 0.1217, comma 0.20633. Before we round the answer, that's the confidence interval we have. The values are in the calculator. Yeah, exactly. Same values. We don't have to repeat entering those values, right? Do you have the same interval though? Do you have the same interval? Okay, awesome. Thank you. Thank you guys. Same interval. Perfect. Yeah. And does the interval include a zero? The interval does not include a zero. Actually, the interval, the whole interval is to the right of zero, right? Yeah, it's to the right of the zero. That means because we're doing P1, we're trying to test the claim P1 is bigger than P2. So P1 minus P2 should be bigger than zero. That's our original claim, right? Yeah. Turns out, although in general, the confidence level, confidence interval method is not equivalent to the two hypothesis tests, but in this specific case, they do have a consistent result. We support the claim because the difference of the P1 and P2 is bigger than zero. It's bigger than zero. All right. It not always happen. Yeah, it doesn't contain zero. It doesn't always happen, but in this case, they happen to be consistent. So I think this question is this one. Oops, I lost it.
So if the confidence interval includes zero, then you accept null as true?
That's a good question. If the confidence interval includes zero, that means there's a chance the null is true. There's a chance the null is true. So we would say fail to reject null. You fail to reject null, right? Because there's a chance they could be equal to each other. Does that make sense?
Yes, thank you.
Yeah, okay. Yeah, I'm trying to find the original problem because we have I think I lost it. Yeah. Well, this is the interval. Yeah, so you can interpret the result as we have a sufficient evidence to support the original claim because it does not include a zero. So we reject no. All right. Yeah. So this is a good question. And this question, for this question, we applied all the three methods. Yeah. Two things very important. First thing, normally when we test the two proportion, the confidence interval method is not equivalent to the hypothesis test methods, the two hypothesis test methods. But in this case, they are consistent. Yeah, sometimes they could be consistent. And second thing, the confidence level, very, very important, very, very important. If the test is a one-tailed test, we must use 1 minus 2 alpha. Do you see the bright purple color? We must use 1 minus 2 alpha to find the confidence level. Yeah, because we do need the confidence level, and then go to the calculator to apply 2 proportion z interval to get a confidence interval. All right, it's okay. We have more questions. Need to use this part. Yeah, I believe when we use more times, you would remember that, right? Okay. All right, so that's 9.1. I think we should move on to 9.2. Section 9.1 is about two proportion tests, and section 9.2 is about the two population means. Two population means, and suppose the two populations are independent. So the samples we got from the two populations would be independent as well. Yeah, so here, independent sample, because later on Thursday, section 9.3, we are going to learn dependent samples would be different. Yeah, so here, independent sample. And we want to know what kind of samples are independent, what kind of samples are dependent, right? Well, let's read the definition here. Two samples are independent if the sample values from one proportion are not related to or somehow naturally paired or matched with the sample values from the other population. Yeah, so if the two samples are independent or dependent, depends on the two populations. I like to use two variables to represent the two populations, like x and y. Sometimes I use x sub 1 or x sub 2. Yeah. So if the two populations are independent, then S1 is from the first population, S2 is from the second population. They must be independent. Yeah, independent in a sense, the values from population 1 and the values from population 2 are not related or somehow paired or matched. And the second paragraph, two samples are dependent if the sample values are somehow matched, where the matching is based on some inherent relationship. That is, each pair of sample values consists of two measurements from the same subject, such as before and after. Yeah, that's very common. Before and after. In next section, you're going to see a lot of those. Or each pair of sample values consists of matching pairs, such as husband and wife. Yeah, where the matching is based on some meaningful relationship. Okay, so today we focus on independent samples. That means the two populations, the values from population 1 and the values from population 2, they are not related or matching. Okay, yeah, notation. Notation pretty straightforward. We know mu is the population mean, x bar sample mean, s sample standard deviation, sigma population standard deviation, n sample size. If I put a 1 sub 1 sub 1 sub 1 sub 1 sub 1, and they are the statistics and the parameter for population 1. If I change those subs to 2, then they would correspond to the second population, right? Yeah. So that's pretty straightforward. And since we are testing mean, what happened to the population standard deviation? We're gonna assume since we're testing for mean, we're going to assume sigma sub 1 and sigma sub 2 unknown. And they are not equal. Okay? Yeah, that's why we cannot use a z-test anymore. We have to use a t-test. We have to use a t-test here. Yeah, let's read the requirement. We have to use a t-test. Requirement include the following 4. Number 1, the values, okay, it's right here. The values of sigma 1 and sigma 2 are unknown, and we do not assume they are equal. Yeah, that's what I just wrote. Yeah, that makes sense, right? Because we're testing mu1 and mu2. Normally, if you do not know the population mean, you should not know the value of the population standard deviation. Yeah, so this is a very reasonable or common case assumption. Yeah, we assume sigma 1, sigma 2 unknown, and they are not equal. And number 2, the 2 samples are independent. Yes, also very important. For the dependent one, we look at in section 9.3, next section. Number 3, both samples are simple random sample. Yeah, we have seen that a lot, right? Number 4, either or both of the conditions are satisfied. Either the sample size both bigger than 30, or the sample come from populations are roughly normally distributed. So those 2 conditions guarantee the central limit theorem. All right, yeah. So this section is pretty close to section 8.3. Very close, but different, because this one involves 2 populations. And the hypothesis tests for 2 population mean, the null is always mu1 equals mu2. Yeah, you might remember in the previous section, when we test the claim about 2 proportions, the null is always P1 equals P2, right? Yes, similar here. When we test a claim regarding 2 population means, the null is always mu1 equals mu2. All right, so those are pretty not very challenging. And the challenging part of the formulas, I will not make you to remember them. Yeah, all you need to know is a t-test. That's all we need to know. It's not z-test because the sigma is unknown. Remember, when we replace the sigma with s, replace the population standard deviation with the sample standard deviation, the variable changes its distribution, changes from normal to t, student distribution. Yeah, that's all we need to know. Yeah, so since it's a t distribution, we have to know the degree of freedom. An easier way to find the degree of freedom is this one. Smaller of n sub 1 minus 1 and n sub 2 minus 1. And there's a, I remember there's a more complicated case. Yeah. And that's enough for us. That's enough for us. So let me highlight. All we need to know, this is a t-test. And we also need to know how do we find the degree of freedom. Okay, the best way to learn this section is to use the technology, right? Yeah, to look at examples. All right, let's see the first example. The first example is about dependent sample or independent sample. Let's read the question. Determine whether the samples are independent or dependent. What sample here? A dataset includes the age and marriage for 130 randomly selected married couples. Cut off this part. Married couples. Okay. Read A, B, C, D and let me know what would you choose. When I see married couple, right? Husband and wife. Yeah, it's actually in the definition. D. Awesome. Thank you, Kelly. I agree. It is D because husband and wife, the values match, right? And very meaningful relationship for sure. The samples are dependent since there is a natural pairing between the two samples. Question number 2, example 2. Large samples of women and men are obtained, and the hemoglobin level is measured in each subject. Here is the 95% confidence level for the difference between the two population means, where the measures from women correspond to population 1. Okay, let me write it down. Women. Let me write female. Female is population 1, right? So mu 1. Male, population 2. So mu 2 is about population mean. We know that the measures from women correspond to population 1 and measures from men correspond to population 2. We know that the confidence interval for mu1 minus mu2 is negative 1.76 as the left endpoint and negative 1.62 as the right endpoint. Yeah, there's a purpose I put this question here. All right, yeah. So this question designed differently from other questions. It is given that the confidence interval for mu1 minus mu2 is from negative 1.76 to negative 1.62. And what are we trying to do is, read part C. Express the confidence interval with the measures for men being population 1 and measures from women being population 2. So now it asks us to switch mu1 and mu2. So they want us to make mu1 as mu2 and mu2 as mu1. So basically switch the order of mu1 and mu2. And what should we find the corresponding confidence interval? Yeah, let's see how do we do that. So they want mu2 be the first population mean, mu1 be the second population mean. So basically, they want us to find, the question wants us to find a mu2, the confidence interval for mu2 minus mu1. Do you agree? Yeah, I want to show you how do we process this question because it's different from all other design-wise, all different from other questions. So basically, we are looking for the corresponding interval, the confidence interval corresponding to mu2 minus mu1. Yeah. If you have a good foundation for algebra, this question would not be a problem with you. But if you have already, forgot the inequality, this would be a problem. So this is what we're gonna do, okay? This is a compound inequality. It has 3 parts, left side, middle, and the right side. And we are going to multiply all the 3 parts in the compound inequality by what? By -1. And you want to remember, when you multiply an inequality, both sides of the inequality by a negative number, you have to switch the order of the inequality symbol. Yeah, if you remember algebra, then you should know that. Yeah, so we are going to multiply the left side by -1, so I have a positive 1.76, and then multiply the middle by -1. If I multiply mu1 minus mu2 by -1, by this -1, I would have mu2 minus mu1. Yeah, actually mu1 minus mu2 and mu2 minus mu1 are opposites. So in the middle, I have mu2 minus mu1. On the right side, negative 1.62 times -1, I have positive 62. But not done yet. Remember, when you multiply an inequality, all the parts in an inequality by -1, negative number, you have to switch the direction of the inequality symbol. Okay, yeah, so that's how you transform the inequality. So this inequality become to 1.62 is less than mu2 minus mu1 is less than 1.676. So we should choose this one. Yeah, it's about algebra. It's actually about, yeah. Do you think you can understand that? Of course, we don't have the time to go over too much about algebra. You enroll in this class, that means you pass the algebra, right? Foundation. Any questions? Let me repeat the rule. When we multiply all the parts in an inequality by the same negative number, we have to switch the direction of the inequality symbol. The direction of the inequality symbol is this way, right? The alligator chasing the stuff on the right. But after we multiply all the three parts by -1, you have to flip the direction. You have to flip them like that. All right? Okay, let's see if you understand that. You don't understand that? Thank you for reviewing. Algebra was a long time ago. Okay, so how about this, Kelly? We all know this is a true statement, right?
Sorry, I was replying to the nope, I got it, of just like, you asked if we didn't get it,
sorry.
and so you're fine. I can understand the confusion. Thank you.
Let's quickly go over this. We all know 1 is less than 2 is a true statement. What if we multiply each side by -1? Then the left side, we would have -1. Right side would have -2. Which one is bigger? -1 is bigger than -2, right? Do you see this? The inequality symbol has to be flipped. That's the reason. You have to flip it. All right. If you have any question, you can actually ask me or email me. Yeah. So this is a part of the question number 7 in section 9.2. I think that it's necessary for us to go over it in a class, because it's kind of actually is a play with inequality. Is a play with inequality. All right, next example. Oh, I forgot to tell you that when it comes to test the claim regarding two population means, all the three methods, critical value method, p-value method, and the confidence interval method, are all equivalent. Okay? Yeah, let me repeat it. When it comes to test the claim regarding two population means, all the three methods, critical value method, p-value method, and those two are always equivalent, right? But in this case, including confidence interval method, all the three methods are equivalent. So they always have you give you the same result, either all reject no or all fail to reject no. Okay, we are going to use all the three methods for this question. Example 3, a study was done using a treatment group and a placebo group. The results are shown in the table. Yeah, the treatment group is population 1, sample 1 actually. Placebo group is sample 2. Assume the two samples are independent. Okay, that's what we want. Simple random sample. Very good. Normally distributed. Right? Yeah. All the requirements are met. Even it did not mention population standard deviation, we assume they are unknown and not equal to each other. Do not, okay, it's here. Assume that the population standard deviation are, do not assume. Yeah, so all the four requirements are satisfied. Use a 10% significance level to test the claim. Okay, what's the claim? Claim that the two samples are from populations with the same mean. Okay, let's see what's the original claim. Claim that the two samples are from two populations with the same mean. So we claim mu1 and mu2 are equal to each other, right? Yeah, so that's the original claim. That's the original claim. Based on the original claim, we can find out what's null and alternative. The null, remember, always equal. It always contains equal sign. So the original claim, so the null is the same with the original claim. Is mu1 equals mu2, and anyone can tell me what's the alternative here? Very important for alternative because what type of test depends on alternative. Not equal. Very good. Not equal. That means this is a two-tailed test. Yeah, two-tailed t-test. Two-tailed t-test. Okay, so let's see what kind of function we can apply in a calculator. Let's see if you can guess. Let's go to stat and tests. Population, two population mean, right? And two population mean, and it's a t-test. What do you think? Which one do you think is gonna be? Yeah, go through the menu, and which one? It has to be t-test, by the way. Two sample t-test, right? Two sample t-tests. Two sample t-tests. Oh, not t-test. T-test is for one sample. T-test, we have two samples, right? Yeah, t-test is in number 2, but we don't choose that. We would try number 4. Two sample t-tests. Two sample t-tests. Yeah, let me write it down. Let me test you. Message here. Two sample t-tests. Let's see what do we have in the menu here. Yeah, it has data and it has the stats. Yeah, we do stats. Okay, choose stats. We don't have the raw data given here. Instead, we have stats here. Okay, we are going to enter the values for x1 bar, s sub x1 sample standard deviation, n sub 1, and we're going to enter x sub 2, yeah, bar, yeah, sample mean, second sample mean, and second standard deviation, and the second sample size. And for the type, we have, you would see not equal to mu2, less than mu2, and bigger than mu2, 3 options, right? Yeah. And then pooled, you have 2 options here, no pool and yes. Yeah, no and yes. And then after that, we have calculate. Yeah. So this is what you see in a calculator. Let's enter the value for those entries. We have x sub 1 bar. We have x sub 1 bar 2.39. Be very cautious. We really didn't do anything else. All we do is enter the values. So make sure we enter the values correctly. X1 bar 2.39. Sample standard deviation for the first sample 0.89. Sample size 28. For the second sample, mean is 2.61. Standard deviation is 0.56. Sample size is 1. And it's a two-tail test, right? We're going to choose this one. Highlight this one. And then always choose no pool. We do not put them together. There's no reason, because they are independent. Yeah, it's a requirement for this type of test. So there's no reason to pull them together. So always no pool. Okay, let's see. Let me enter those values first, and then I'll show you what I have. X1 bar 2.39, 0.89, 28. Yeah, the sample size only 28, shy less than 30, but it doesn't matter because the population is normally distributed. X sub 2, 2.61, 0.56, and this is a 31. So conform, select and conform two-tail test, and then no pool is defaulted as no pool. So calculate. Okay, so I'm gonna tell you what I have. I got T test statistic T equals negative 1.122603,653, and the p-value equals 0.26, 7602676 94 162. And degree of freedom, we don't even have to enter the degree of freedom ourselves. You know why? Because the calculator programmed, they will use n sub 1 and n sub 2 to find out the degree of freedom, right? As you can see, the degree of freedom is not a whole number. Yeah, the formula we see earlier, the formula I shown you is a brief or shorter version, is a convenient version of formula. But actually, there's a more complicated but accurate formula for finding the degree of freedom in this type of test. But we don't have to worry about that. We do not have to worry about that. Okay, guys, please let me know. Do you have the same thing? Do you have the same test statistic and the p-value? Awesome, awesome, very good. Thank you, guys. Well, as I said, I would not, unless I was asked to find I have a different p-value. What's your p-value, Miranda? I have a 0.2676. That's 0. Did that confuse you? 94162. 866. Oh, that's very different. You want to double check and go back, look at the entries. Do you enter the exactly same entry, or did you select and confirm is a two-tailed test? Right here, you have to confirm, not just blinking there, and you have to confirm and make sure when you go down and the not equal to mu2 is still highlighted. Okay, you did that. Can you double check your entries? Those values, make sure they are the same with mine. I put a 33 instead of, oh, okay. It's okay. That happens. Yeah, so really be careful and mindful. Yeah, always, to be honest, all we do is to enter those values in the calculator. And it is very lazy way. So we need to at least make sure that the values we enter to the calculator are correct. Well, we are not done yet. So that's how we apply the hypothesis test to test the claim about the two population means, right? And now we want to use confidence interval test. Yeah. So what kind of function we're going to apply for confidence interval test? Let's go to the stat and test again. Two samples, right? And it's t test, so it's gonna be t interval. Two sample, two sample t interval. Yeah, it has to be that one. Two sample t interval. Yeah, so for applying the confidence interval method, we use, I have 0 here, two sample t interval. All right. Yeah, make sure you have the same function found. Yeah, that's what we're gonna use for the confidence interval method. Yeah, let's select that two sample t interval. And also let it stay as stats, right? Yeah. There's two options, data and stats. We are on stats because we are given stats. We don't have the raw data. As you can see, those entries are already there, right? Same with earlier, same with 9.1 earlier. Yeah, x1 bar, s x sub 1, n sub 1, and so on. Yeah, those entries are already there. You don't have to do it again. Well, confidence level, very, very important. Help me out, guys. What's the confidence level supposed to be? Two-tail test, not one-tail test. Two-tail test. Significance level is 10%. It's right here. And what's the confidence level supposed to be? Wow, it's too red. Confidence level is supposed to be two-tail test. Two-tail test. Significance level is 10%. What about confidence level? Yeah, this time is 1 minus alpha. 90%. 90%. Confidence level is 10%. Yeah, 0.9 or 90%. Very good. Very good. Am I clear? I want to make sure everybody is aware of this. I know Kelly definitely is aware of this. So when it's two-tailed, is really confidence level is the complement of the significance level. You know, what is a complicated part, what is special is when the test is a one-tail test, either left tail or right tail, then you have to use this formula, 1 minus 2 alpha, to find the confidence level. But in our case, in this specific question, two-tail test, so just the 1 minus alpha. Okay, when you do your homework, you probably remember to go back here and look at it. Okay, so let's see what interval we would have. Let me enter confidence level 0.9. I have 0.9 there already for some reason. We do not pull and calculate. My confidence interval is, without the rounding, yeah, you round it yourself, negative 0.5492. The right end point is 0.10918. Yeah, you should have the same confidence interval, guys. Yeah, let me know, do you have the same? Awesome. Well, we do those tests, we have not talked about the conclusion yet, right? All right, let me see what's my p-value here. Okay, my p-value is 0.26, almost 27%. Is high, is bigger than significance level 10%. So p-value is high, no must fly, fail to reject, no, right? Yeah, if we use critical value method, it's gonna be the same, fail to reject, no. And also, let's look at the confidence interval. Does the confidence interval include a zero? Does the confidence interval include a zero? Yeah, zero is in it, right? Yeah, it does. It does, that means there's a chance that the no is correct. Yeah, based on our sample, the no is correct. Only one sample, of course, you can only say fail to reject. You would not say support. Yeah, very subtle, because we only have one sample. Fail to reject, no. So in this case, you can see all the three methods, yeah, are consistent, and that is in general true. When we test the claims regarding two population means, the three methods are always equivalent. Yeah. Here we fail to reject no. Is it possible? The no is correct. Yeah. But of course, if you want to make sure, you have to do more tests, right? Get more samples. Well, based on our sample, we can only say we fail to reject no. Since we fail to reject no, we have sufficient evidence to warrant the rejection. We have we do not have sufficient evidence to warrant the rejection of the no. So look at the table, the four conclusions. You fail to reject no, then you fail to reject the original claim, right? There's no sufficient evidence to warrant the rejection of the original claim. All right, guys, we're gonna skip example 4 because it is the same type, and we are going to go ahead to look at this example. Example 5 is different, okay? Why different? We have two samples here. Listed in the data table are IQ scores for a random sample of subjects with median lead levels in their blood. Also listed are statistics from a study done of IQ scores for a random sample of subjects with high letter levels. Okay, so here we have two samples from two populations. That's the sample 1, that's the sample 2, right? Yeah. Median letter level, sample 1, high letter level, sample 2. We assume the two samples are independent. Yeah, that's what we want. Simple random sample, that's what we want. Normally distributed, that's what we want. And of course, the standard deviation, yeah, unknown are not equal. Yeah, so those 4 requirements are mentioned, and they are all satisfied. So when we need to use, yeah, this is the problem. The reason I put this question here. When we use the formula, when we use the function to sample t-tests, yeah, let's go to the calculator. When we go to the function to sample t-test, number 4, we have 2 options, right? Data and stat. And which one should we choose? And this one is special because one group, one sample, we have the raw data. The other sample, we do not have the raw data, and we have the statistics, mean, sample standard deviation, and sample size. And what should we do for that? We should use stat. You know why? Because from the raw data, we are able to find the statistics, like sample size. How many? Let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So sample size for the first sample is 11. And also, if we add them up, add all the 11 numbers up, and then divide by 11, we would have a sample mean. And we can use the formula, we use the calculator to find the sample standard deviation. Yeah, but we cannot go from stats back to the raw data. That's the reason we use stat. But before we apply that function, we have to firstly enter those values in list 1 and then do the calculation. Okay, would you like to do that with me? So let me explain what's going on here. All right, yeah, we cannot use data because if you use data, you have to have both samples are raw data. You cannot do half and half. Yeah, you have to keep consistent. And since we cannot go from stats back to raw data, but we can go from raw data to stats, we're going to use stats here. And before that, we need to go to stat, edit, okay, stat, edit, and I have something in my list 1, I'm going to clear them, and then enter the 11 values there. So I'm going to enter 72, 97, 92, 85, 89, 97, 83, 92, 98, 111, 91. All right. Yeah, make sure you have the 11 values entered in list 1. Yeah, I don't really keep those values, so I always use list 1. And then we go to stat, and then shift to the right twice. Shift to the right once. Calc, and click the first function in the menu. Calc one variable stats. Yeah, this is from a long time ago. We learned this a long time ago. So we would see list, right? you're gonna enter list 1 there. Ask me if you don't know how to enter list 1. And keep frequency list empty and calculate. And I want to ask you, do you have X bar equal to 91 point, your X bar, your sample mean is 91.54, 54, 54, so 54 repeating, right? Is a rational number. And your standard deviation, S sub X, is 9.923342545. Yeah, more precise, your S sub 1 is 9.923342545. Your N is 11. Yeah, I want to know if do you have the same thing? Guys, do you have the same thing? Yeah, they are not given. Awesome. Yeah, they are not given, so we have to do them, find them ourselves. Yeah, I know it's a little bit troublesome. Yeah, but it's not given. We would have to do that on our own. And now we're ready for the function application to sample t-test. Use the stat. Okay. Now we go to stat. Yeah, I'm gonna go to second mode first and then go to stat. Tests to sample t is t-test. And x sub 1, x1 bar is 91. I'm gonna enter 91, 54. 54. Yeah, I keep it as precise as possible. And my standard deviation for the first sample, 9.9233425. N sub 1, 11. X2 bar, 90.355. Oh, you know what? Actually, I forgot to tell. So since the X sub 2 and S sub 2, I would round X sub 1 bar same with X sub 2 bar. I would round S1 same with S2. So since X2 bar 3 decimal places, S2 also 3 decimal places, I think it's reasonable to round this one 91.545 and round this one as 9.923. Yeah, that should work. Yeah, let me go back to fix it. 91.545, round 3 decimal places. Same with the second sample. S sub 1, 9.923. And this one is 11, and this one is 90.355. And this one is 9.794. N sub 2 is also 11. Double check. Yeah, very important to double check your entry. 91.545. 9.923, 11, 90.355, 9.794, and 11. Okay. What kind of test this is? We have not determined that yet. What is the original claim? Oh, it's right here. Claim that IQ score for median is higher. Okay. So we're testing mu1 bigger than mu2. All right, we're testing mu1 is bigger with median level higher than the median. Of course, you don't want a lot of lead in in the blood. So our no is equal. Our alternative is bigger than, so this is a right tail test. Right tail test, so we're gonna select bigger than mu2 and confirm it, and no pool and calculate. All right, I'm gonna give you my test statistic and the p-value. My test statistic t equals 0.2830793375, and my p-value pretty high. P-value is 0.3900128887. All right. Do you have the same thing, guys? Yeah, my p-value pretty high, almost 40%. Yeah, compare with the given significance level, 10%. We are going to fail to reject no. Awesome. Yeah, fail to reject no. Well, let's try the interval method, confidence interval method. Anyone can tell me what's the confidence level? Very important. Anyone can tell me what's the confidence level? In this case, by the way, this is a right tail test. Alpha is, oh, it's not 10%, it's 1%. Alpha is 1%. So what's our confidence level supposed to be? Subtract that from 1, 98%, right, Kelly? 98%. I misspoke that. 98%, right? Yeah, 98%. Yeah. So our confidence level should be 98%. Everybody, is that clear about the confidence level? Yeah, please let me know. Otherwise, I feel very guilty. You messed up this part. Confidence level 98%. Why? Significance level is 1%. Why do we use 100% to minus twice of 1% to get a confidence level? Because the test is one tail. We have to do that to make it symmetric. Okay, guys, please let me know. Do you understand why the confidence level is 98%? Huh? Melinda, how come it's not 99%? Yeah. Because the test is a one-tail test, so it has a significance region, critical region on the right side. Critical region on the right side has an area 1%, but now we are trying to use confidence interval method. We have to make it symmetric. We have to make it symmetric, so we have to make the left side also have a 1% critical region. Yeah. So it's one tail t-test, right? We have 1% here. But since we are using confidence level, a confidence interval method, we have to make it symmetric. So we have to have 1% here as well. Because the confidence interval is symmetric. The more complicated the proof, it doesn't really help us. So the confident part is only 98%. All right, 98%. Yeah, Melinda, understand that? Awesome. What about other people, please? Am I drawing your attention here? Yes or no? Okay, thank you, Dustin. It's very, very important. Very, very important. Thank you, Kayla. Miranda. Okay, when you do your homework, if 1 minus alpha doesn't work, please go back the video today. Okay? Yeah. when it's a one-tailed test, you have to use 1 minus 2 alpha to find the confidence level. Okay, we run out of time. One more thing, this question, the last one. This question, we're going to use data. Okay, you're going to enter those values for L1, those values for L2, and then in the function, you use data, L1, L2, and then you can find the test statistic and the p-value. I think you can figure it out on your own, okay? The confusing one is half, like this question. Yeah, one sample is stats given, the other sample is raw data is given. Yeah, so we go from raw data to stats. Okay, guys, so that's everything about 9.2. If you have any questions, please feel free to email me. I would say good night. On Thursday, we are going to go over 9. Let me take a picture of attendance. I think we have one more participants. It was 8 people. Now it's 9 people. Thank you guys for coming. Yeah, good night, everybody.